All right, let's get started. Welcome everyone to come our TrustML scientist seminar. Before that, I'm going to introduce our valuable guest today, Dr. Lee. Linghie is a fifth-year PhD student in computer science at UIUC. He is co-advised by Li and Tao Xie. His research lies in the intersection of deep learning, security, and software engineering. Especially, he designed algorithms for certifying desired properties, such as robustness of deep neural networks and methods for training certifiable deep neural networks. He's a finalist of 2 Sigma PhD Fellowship at Qualcomm Innovation Fellowship and a recipient of Wing Kai Chen Fellowship at UIUC. Prior to the UIUC, he received his bachelor degree in computer science from Tsinghua University, China. Let us sincerely and welcome Linghie to give us a talk. Hi, Linghie, please proceed.
Yeah, hi. Thank you for the nice introduction and nice hosting from Jinfeng. And hello everyone. Yeah, as Jinfeng introduced, I'm Lee Li, a first-year PhD student at UIUC. So today I'm going to talk about the state of the art and our serious work in the direction of large-scale, certifiable, trustworthy machine learning. Feel free to interrupt me if you have any questions. I plan to make this talk more interactive. So let me proceed. So I plan to organize this talk following this structure into 3 parts. First, I'll introduce the background and the state of the art on certified robustness for deep learning, which covers popular certified robustness approaches, including linear bound propagation, Lipschitz-based robustness, branch and bound, and randomized smoothing. Our work is built upon these existing works. Then I'll introduce our series work towards generalizing certified robustness methods for trustworthy ML in the real world. Our efforts can be divided into these 3 aspects. We provide tighter and more scalable certification. We propose more effective training methods, and we also generalize the certification methods that were designed for robustness to a more rich set of properties, including semantic robustness, distributional robustness, and fairness. The last part of this talk will be a discussion of challenges and the possible solutions in the whole field of certified machine learning, including some core questions that to be solved and possible directions to think about and to solve it. So then let me proceed. Yes, if you have any questions, just feel free to ask and interrupt me. So a bit on background. Neural networks are vulnerable to adversarial attacks, as we all know, where small imperceptible perturbations can fool the model to make wrong predictions. So throughout this issue, there is an arm race between the defenders and attackers, which is one of the main topics over the years, where the attackers and defenders are attacking and defending their counterparts adaptively. So can we end this game? The research on certified robustness may provide a possible answer. So certified robustness can be divided into robustness verification and robust training approaches. So the robust verification or certification approaches verify that for a given neural network model and a clean input, whether the model is robust within a certain perturbation radius. So, and then the robust training approaches train the neural network model in a particular way so that the robustness verification or certification methods can verify it to have a good robustness. So the arms race can be ended by certified robustness approach because if the verification finds that there is no adversarial example, then it means that any future possible attacks are destined to fail. So then let me start with a precise definition of certification problem that are commonly studied in the literature. Consider a classification model with input X and the ground truth label Y. So the certification goal is to check that whether for a given perturbation delta, as long as the LP norm of the perturbation delta is bounded by some predefined threshold epsilon, the model's prediction does not change. If the model is not robust, the certification method should always output false. So it can be called as a certification of robustness. And if the model is robust, given this input, we hope that the certification or verification method can output true as much as possible. So then it could be called as a tight certification method. So in our recent SNP 2023 paper, we make a comprehensive taxonomy of recent current verification and certification approaches for neural networks. They can be classified as shown in this big tree. So I'll briefly introduce 4 types of verification methods that are commonly used nowadays. They are linear relaxation methods, branch and bound methods, Lipschitz-based certification, and randomized smoothing methods. The linear relaxation method is extensively studied. Combined with the branch and bound regime, it achieves state-of-the-art robustness certification efficiency for given neural network models. And then the Lipschitz-based approach includes Lipschitz-bounded model and includes the Lipschitz-bounded training. So such Lipschitz-based approaches achieve state-of-the-art certified robustness on common data sets if combined with the specific training approaches. And then the randomized smoothing approaches bring a probabilistic robustness guarantee, and they are more scalable than other approaches. Indeed, the randomized smoothing approach is the only type of approaches that achieves certified robustness on the large ImageNet sized data sets. So yeah, let me start with the linear relaxation approach, since this is the most straightforward one. To study the linear relaxation methods, we first formulate the structure of a typical neural network. A typical neural network has a layered structure as shown in the left figure. So the first layer is in the input, then each layer executes a fine transformation and then impose an activation function for each component of each layer. Usually, the activation function is a ReLU function. And then the last layer has C components that corresponds to C classes. They are the confidence score of each class. So the model will predict the class with the highest score among the C scores. As we can see, the only non-linearity of neural networks comes from the ReLU activation. So then to verify the robustness, now the most important thing we need to do is to deal with this ReLU activation. So as shown in the figure, for the ReLU activation, we can bound its output by a lower line and an upper line. So this is called the linear relaxation for the ReLU activation function. So with such linear bounds for all the ReLU functions in this deep neural network, then we can propagate a linear bounds through the layers of the neural network, so that the output of the network can also be linearly lower and upper bounded. This is called the linear relaxation approach, and this approach is the most widely used verification method for general networks. To see why these linear bounds can be used to verify robustness, we can imagine that given such linear bounds of the output layer, we can see that we can inspect that whether the lower bound of the ground truth class is always higher or equal to the upper bound of all other classes. If this condition is satisfied, we can see that for this input after perturbation, for any perturbed input can always have this property that it will predict the ground truth label. So as we can see, this type of approach is kind of loose, although it has high efficiency. So for very large or very deep neural networks, such as those for ImageNet, it becomes loose and hard to verify the robustness. So later I will show an approach that can deal with large data sets and large models. So here we mainly consider how to tighten such verification. To tighten such verification, a common regime is called branch and bound. The branch and bound method is a type of complete verification method. It means that such verification of neural network has no relaxation. For robust instance, given sufficient time, this type of method is guaranteed to always output certified. So this requires the method not to have any relaxation, and it is proof that complete verification is a quite challenging problem, and it is indeed an NP complete problem. So a common framework to solve complete verification, as I said, is the branch and bound. In branch and bound framework, we select some random neurons to fix at the inactive and active stage, and then solve the corresponding two subproblems corresponding to these two constraints. So under each constraint, it means that under each inactive or active constraint, the behavior of the neuron becomes linear. Then we can relax other neurons by the linear bounds and solve the corresponding linear programming problem. If the problem solved is robust, then the robustness is verified. Otherwise, we can further fix more neurons to be active or inactive and go in and deeper into the split tree until the robustness can be verified or not verified. So currently, instead of solving the expensive linear programming problem, we can also replace the linear constraints, which shown here, by linear inequalities, as I discussed in the last slide, and as shown in this right figure. So after this replacement, we can see that for each neuron, the bound becomes looser because the blue region becomes larger. It means a larger relaxation. However, these linear inequalities allow us to quickly propagate the bound through the network in batches. So we can get rid of the expensive instance-wise linear programming solving. Furthermore, such bound relaxation allows us to use gradient optimization to find the best slope of these relaxations so that it can give us tighter inequality bounds. So following this line, the current the current state-of-the-art verifier, alpha beta cron, is built upon this branch and bound plus linear relaxation plus batched bounding process. So we can see that although the bounding part becomes looser because of the use of linear relaxation instead of linear programming, because we're able to visit more branches, it eventually becomes more efficient. Actually, the current state of the art, recently there are two verification competitions, namely WinNComp 2021 and 2022. And this type of regime achieves the highest efficiency and becomes the winner for both for both competitions. And this verifier will be open source in September. So this is the line of research towards tightening the robustness verification. And there's another line of research towards achieving highest robust accuracy by combining both verification and training. So a way to achieve so is called Lipschitz bound. We can see that because the classification model takes the label with highest logit as the output, therefore, we can divide the logit margin by the Lipschitz constant to get the robustness radius. So, and the Lipschitz constant can be computed by computing the multiplication of all the spectral norm of the weight matrix in the model. So actually, we can design several regularizers to train neural networks to have small spectral norm. And actually, Professor Sugiyama's work at NIPS 2018 is a pioneer work towards this line of research. And then recently, people start to think about how to achieve Lipschitz bound, not from training and regularization perspective, but from the architecture perspective. The most recent breakthrough towards this direction is the proposal of L-infinite net. The L-infinite net is a type of neural network that uses z theta, this type of function as the activation function. We can see that this activation function has one Lipschitz under L-infinite norm. So it means that the model constructed by this activation function naturally has certified robustness under L-infinite norm. Combined with an optimized and tailored training approach, this architecture can achieve state-of-the-art robustness on MNIST and Cypherton datasets. However, it still cannot achieve certified robustness on large datasets like ImageNet. So to handle ImageNet, another type and the popular certified robustness approach is called randomized smoothing. In randomized smoothing, it slightly changes the inference protocol of the neural network. Here is the high-level idea of randomized smoothing. First, we train a neural network under Gaussian noise corruption so that the model can still work relatively well for Gaussian noise inputs. Then we smooth F into a new classifier G. G samples multiple random noises and adds them to the input. Then it predicts the most probable prediction by F under noise. For example, consider a panda image X. With Gaussian corruption, the model F actually classifies the Gaussian distribution centered at X. Suppose that there is an 80% probability where panda is returned, 15% probability where a gibbon is returned, and 5% probability where a cat is returned. Then, since panda is the most probable class, we return Gx equals to panda. So the main insight of using this Gaussian smoothing and voting is that if we slightly shift the center of the Gaussian, the probabilities of each class cannot change too much, given the largely overlapped support between the original Gaussian and the slightly shift Gaussian. So as long as we just slightly shift X, in other words, as long as we just add small perturbations to X, the ranking of different classes does not change. So the panda is still the most probable class and has higher probability than gibbon and cat. So we are still robust. So the prior work has given this type of robustness guarantee that as long as the perturbation is within R under L2 norm, the prediction is guaranteed to be the same. To compute this R, we need to know PA and PB, which are the probabilities of top class and run-up class. So to compute PA and PB, we usually use Monte Carlo sampling, which gives us a high confidence bound for PA and PB respectively. It doesn't require expensive bound propagation or branch and bound to verify the robustness, but as a cost, the robustness certification is probabilistic due to the high confidence bound of PA and PB. And as a result, because we don't need a branch and bound and we don't need bound propagation, so randomized smoothing is much more scalable and can be much more easier in terms of handling large sized models. actually is the only approach that can give us robustness certification on ImageNet dataset. So our research thus mainly focused on improving and generalizing the randomized smoothing based certification due to their scalability. So to conclude this part, let me give you guys a summary of the state-of-the-art certified robustness leaderboard. So on the ImageNet dataset, we can see that the certified robustness accuracy is already over 93%, which is satisfactory, given that each pixel allows for 30% of brightness change. So, however, on larger dataset, the gap becomes slightly larger. For example, on Cypher 10, there is still a lot to be done because under the L infinite norm with only 8 over 255 perturbation radius, the certified accuracy is just about 40%. And the empirical accuracy against very strong attacks can be over 65%. So 40 versus 65 means that there's still a large gap that we need to solve. So also 40% is still far from satisfactory for model to be used in practice. And then on even larger dataset like ImageNet, the situation becomes even more severe. Our work actually achieves the state-of-the-art certified robustness on ImageNet. Under L2 norm with radius R equals to 2, the certified robust accuracy state-of-the-art is just slightly above 30%. So later I will introduce how we achieve this state-of-the-art in detail. By the way, I'm maintaining the state-of-the-art leaderboard in certified robustness field in this website. And more progress summary is in our paper published at SNP 2023. So this is the end of the first part. Do you have any questions?
Actually, I have a question on the random smoothing. I just wondering, since the input is high dimensional, when we do some random sampling, how do we guarantee we can find the gibbons for Panda? Even with sample 1,000 times or 10,000 times. Yeah, that may not, yeah.
It's a great question. Do you mean that if since it's a high dimensional input, intuitively we cannot sample even similar images, like after adding noise? It's a valid concern. And indeed, in practice, the sampled images are not overlapped, and they can hardly be the same. However, because for each of the sampled image, the confidence is bounded between 0 and 1. Means we have such high confidence lower bound or high confidence bound with Hofding to bound. What will happen if we do another set of sampling? So it means that even though for each round the sampled noise image are almost never overlap, we can still have a high confidence bound of the outcome of such sampling. It's like somewhat magical, but it is true. This is the interval and the finiteness of the output.
Oh, okay, got it. Thank you.
Oh, thank you. Yeah, then maybe we can proceed. So the second part of my talk would be an introduction of our work towards generalizing the certification for trustworthy machine learning. In the first and the second part, we boost the certified robustness guarantee via tighter certification and more effective training. Then in the last part, we generalize the certification for LP robustness to a much broader range of notions. So in the first part, let us recall that the randomized smoothing certification usually computes certified radius R based on this expression in practice. It's slightly different from what I introduced before. It's like we don't compute PB because in practice, we usually set PB equals to 1 minus PA for efficiency concern. So we can see that this equation and certification is simple. However, existing approaches doesn't target at improving this certification almost at all. This type certification radius R is proposed in 2019, and after this radius is proposed, many existing efforts for randomized smoothing only improves the smooth distribution and improves the training process instead of improve the certification radius R's expression. So why this could happen? This is because the certification of randomized smoothing suffers from a theoretical barrier, means that the R that I shown before can be hardly improved. And theoretically, this bound or this barrier says that the randomized smoothing is enabled to certify high infinite robustness with high dimensional input. In other words, the L2 robust radius such as the R that I shown before is almost a constant with respect to the input dimension D. So due to this barrier, further improvements in randomized smoothing becomes marginal. However, we find a blind spot in this story is that all these barriers about the certification aspect of randomized smoothing only considers that the certification methods only use the top class probability information. Instead, we can query more information from the smooth classifier to bypass the theoretical barrier and achieve a tighter robustness certification for randomized smoothing. So maybe let me make this point clear, is that in classical randomized smoothing, the certification is that we apply one-color sampling to get a PA. Then by computing what would the worst case look like, we can derive the certified radius R, which equals to sigma times phi PA, as I shown before. And then to improve the certification part in this work, we find that actually we can leverage much more information instead of just PA. We find that besides conducting one sampling process, we can actually use another distribution Q, and then jointly use the sampled probability PA and QA to derive the robust certification. Viewing from the optimization perspective, in classical randomized smoothing certification, we're actually solving this type of constraint optimization, which where the PA works as a constraint here. And here, in DSRS, our framework, we actually seek for the worst case function that satisfies both PA and QA constraint. And it appears here as another constraint. So with this another constraint, DSRS, our framework, is guaranteed to be tighter than the classical randomized smoothing. So we also conducted extensive theoretical studies of the tightness induced by adding one constraint for certification. We observed that under the concentration property, which generally holds for common classifiers, DSRS can achieve square root D L2 certified radius, which translates to non-shrinking L infinite radius, and thus can circumvent the long-standing L infinite barrier of randomized smoothing. This is the first non-barrier circumventing certification method to the best of our knowledge. And then we also implemented our DSRS certification for randomized smoothing and show its performance in practice. We can see that all the green curves corresponding to the certified radius or certified accuracy produced by our DSRS certification. And we experimented DSRS on MNIST, Cypher10, and ImageNet dataset. We can see that the green curve is consistently higher than the blue curve, which is the classical randomized smoothing certification. And this curve stands for the certified accuracy under the radius R. So it means that DSRS is also significantly tighter than classical randomized smoothing in practice. So this is our efforts and progress on improving the certification tightness towards certified robustness. Do you have any questions in this point? Okay, yeah, then maybe I can proceed. So besides improving the certification for higher certified robustness, we can also get better certified robustness by training. So when it comes to randomized smoothing, since the model predicts the most probable class, we require the probability for predicting the ground truth class, namely PA, for the perturbed input to be as high as possible. So now we consider this PA. For ease of analysis, we approximate this hard probability PA, which is the probability of predicting the correct class under Gaussian noise by a soft smooth confidence, which is the expectation of F, which is the soft confidence score under Gaussian noise. So we denote tilde F to this soft smooth score. Then in this work, our key observation is that for this tilde F, since we use Gaussian smoothing, so this tilde F has a smoothness bound, which is the bound of eigenvalues of the Hessian matrix. So with this smoothness bound that is only dependent by the smoothing variance, we can see that from Taylor expansion, by regularizing the zeroth order term and the first order term, we can rigorously lower bound the tilde F, and thus we can rigorously and effectively enlarge PA just by regularizing the zeroth order and the first order term, because second order terms are already bounded. Then let's look into what does it mean by regularizing the zeroth order and the first order term. So the zeroth order term is actually tilde F at the clean input X. It directly corresponds to a large confidence margin, and it is differentiable, so it is easy to optimize. And here comes the first order term. The first order term actually is the magnitude of the gradient, because we have to guarantee the robustness against any direction of perturbation. So we require the gradient magnitude of tilde F to be small. However, guarantee the magnitude to be small means that we have to hurt the model's expressivity, which makes the model training difficult. So then we found that we can circumvent this barrier by consider an ensemble of F. So consider that if F is not a single model, but is an ensemble composed of F1 plus F2 plus F3, then the gradient magnitude of F equals to the magnitude of vector sum of tilde F1, tilde F2, and tilde F3. So it means that even though F1, F2, F3 may have large gradient, as long as the gradient direction becomes diverse, then after they add together, it's quite likely that the whole vector becomes canceled out and thus results in a small joint gradient magnitude. So the first order regularization boils down to regularizing the gradient diversity among base models within an ensemble, which is believed to be helpful for robustness, also from the transferability perspective. So now, as a result, we can encode our zeroth order and first order terms as two regularizers respectively. They are confidence margin loss and gradient diversity loss. So by combining these two terms together into the training loss, we can train models that achieve state-of-the-art L2 robustness for randomized smoothing, as shown by the purple line, which is significantly higher than other training methods. So besides training and certification against the classical LP perturbation, actually to make a robust model in practice, there are many more rich specifications that the model needs to be satisfy. For example, we believe that another practical threat model is called semantic robustness. Semantic robustness is that the attacker can apply geometric transformations to the image and then feed it into the classifier. For example, the attacker, instead of adding noise that are bounded by LP, now it can pick a rotation angle, maybe within 30 degrees, and then choose to input any rotated image to the classifier in order to fool the model. This type of attacker is quite common in natural. For example, a camera in an autonomous vehicle can take a rotated or scaled image very likely because of the position or of the location of the car. And then, so it's very necessary to certify against this type of attacker. And now we propose a very simple and straightforward strategy to certify against this attacker. So our strategy is called is basically divide and conquer. So it is composed of 3 steps. First, it partitions the perturbation region into tiny sub-regions, as shown here. For example, for the -30 to 30 degree interval, we can partition it to maybe 60 tiny intervals, where each tiny interval has a span of 1 degree. Then we try to rigorously upper bound the maximum LP distance incurred by the transformation within each tiny interval. We propose a method to bound such maximum LPD distance for all images within such tiny interval by transformation and the data-specific Lipschitz bound. So then we trigger the existing LP-based certification and then compare the certified radius with this maximum LP difference. And if this certified radius is larger than the maximum LP distance within each tiny interval, then we can see that the model is certifiably robust against this semantic attacker. We introduced several optimizations in our strategy, and we also make this maximum LP distance bound computation quite general, so that our strategy for the first time enables a high certified robustness against a various set of semantic transformations. So recently, we also generalized this framework to handle point cloud models. This is the first type of generalization we did for the certified machine learning. And then the second type of generalization we did is called distributional robustness problem. The distributional robustness problem is widely studied in OOD robustness and also in the domain transfer community. Here, the certification problem is no longer point-wise certification. Now we consider to upper bound the expected loss under shifted distribution Q, given the expected loss on the original distribution P and the distributional distance between P and Q. So previous work on certifying this threat model considers one system distance as a metric between P and Q. And then they use model Lipschitz bound and the duality to propose a method to compute such upper bound certification. However, the method requires a rigorous Lipschitz bound of the model, which is usually loose and hard to be tightened for common neural networks. And in contrast, our recent work considers the Henninger distance, which is a type of F divergence, as the distance bound metric D. And then under Henninger distance, we can directly leverage the overlapping support inspired by randomized smoothing and semi-definite Gramian matrix to get the certification. This type of certification is much easier to compute, and for the first time get rid of the expensive Lipschitz constant certification, which makes the certificate much tighter and much scalable than before. And then we built upon this work recently. We also found that we can generalize the distributional robustness notion to distributional fairness notion. So our distributional fairness certification certifies the model's worst case expected loss on a fair test distribution, where the fairness is defined by equalized base rate among the protected groups. So now, as we can see, it corresponds to the distributional robustness problem with an additional fairness constraint. So now, this certification can bounce the worst case model's performance in a fair real-world environment. It can also recover the established fairness notion, including odd disparity notion and the demographic disparity notion. So for this type of the distributional fairness problem, we propose an efficient and effective certification strategy. And our strategy is also composed of 3 steps, similar to the semantic robustness strategy. Here, we first decompose the whole distribution into several subpopulations based on the sensitive attributes. Then we apply the distribution robustness bound that I presented in the previous slide to each of the subpopulation respectively. Lastly, we show that the optimization over such bound combinations is a convex optimization problem. As a result, we can formulate a low-dimensional convex optimization problem and leverage existing convex optimization solvers to compute such fairness certification very efficiently. So then, to this point, we have shown how we can generalize the certified robustness approaches to certified robustness against semantic attackers, to distributional robustness, and to distributional fairness. We also generalize it to more notions, and feel free to check out our group website. So this is the end of my second part of the talk. And in the third part, I'm planning to discuss the common challenges and possible solutions in the whole area of certified machine learning. In this slide, I will first categorize existing challenges and research questions in the field of certified machine learning. The research of certified machine learning starts from the certification and training methods for robustness against LP-bounded perturbations. Stemming from this core problem, there are naturally 2 branches of research, which are finding tighter and more scalable certification and constructing models that are more robust and more friendly for certification. The model construction can be achieved by finding robust model architectures, finding effective robust training, and proposing robust inference protocols, or their combinations. The shared core open problem of these directions is achieving close to human certified robustness on large-scale datasets like ImageNet, which we have shown we still have a long way to go. And besides solving this core open problem in this field, to achieve trustworthy machine learning for real-world needs, just achieving LP robustness is far from satisfactory. Therefore, a third branch of research is to generalize the certified robustness notion towards real-world requirements and towards general trustworthy AI. Following this tendency, there's a wide range of properties that are needed by AI, and we may need to analyze how to achieve certifiability for all of them, including robustness against domain shift corruptions, including certification of fairness, privacy, interpretability, numeric stability, controller safety, and detoxifying NLP, and trainability. And lastly, although we have some work and some progress in the certified machine learning field, we see that we haven't seen much of them are applied in practice yet. Actually, there are several challenges for these approaches to be deployed. They include the training overhead, the inference overhead, the point cloud soundness, and more importantly, the benign performance degradation. So these are all very important and core problems in the whole field of certified machine learning. So now let me give you some hints on the directions that may be able to solve them. So first, for better certification methods, we need to think about how to design more effective abstractions for robustness certification. Just as I presented before, for randomized smoothing, we can actually leverage more information which corresponds to a more concrete abstraction of the model, so that we can have a better and tighter robustness certification. This is the general way to derive a tighter certification methods for robustness and for all other trustworthy properties. And then to achieve better certified robustness, we also need better model construction. Maybe it's the Lipschitz bounded architecture, maybe the implicit models or error correction with rule-based knowledge could be a good way to construct an intrinsically more robust and more certification-friendly model. Also, maybe simply scaling the model size, like you using larger models, as Sebastian Bubeck suggests, could also be the key to achieve a more certifiably robust model. And then for the problem of generalizing the certified machine learning methods, the key question is to get a good problem formulation. We intuitively have many properties besides robustness that will require the model to satisfy. However, to derive a certified method, we need to define these properties formally and precisely. For example, what exactly does robustness mean in practice? What exactly does perturbation set should we consider? What exactly does fairness mean? And what exactly does interpretability mean? These are all the core questions. And as long as the formal definitions for these properties exist, then I think solving them or generalizing the existing toolkit to solve them is relatively easy. And then for solving the practical issues, there are also a few possible solutions. For example, to solving the training overhead to achieve certified robustness, maybe we can find ways to robustify the model prediction at the inference time, such as self-denoising. To reduce the inference overhead, maybe which many exist for randomized smoothing, because randomized smoothing needs multiple rounds of voting. Maybe a way to achieve so is to design a specific architecture that can give predictions for multiple noise inputs at the same time. And then to solve the benign performance degradation problem, maybe better training methods or a detection method that can help us to switch between high accuracy and high robustness models could be a practical solution. So this is the end of my presentation, and thank you very much for listening. Any questions and discussions with me are very welcome.
Thank you so much for Linghie's great talk. Hi, audience. If you have any questions, please feel free to ask here. Before that, I have a question. Yeah, what do you think of the current bottleneck, the most bottleneck for certifiable robustness?
It's a very great question. I think the most bottleneck is still the core problem here, that we need to achieve close to human certified robustness on large-scale data sets. We can already achieve close to human certified robustness on small data sets like MNIST, but slightly large data sets, then the certified robustness becomes dropped very quickly. Like on Cypherton, we only have 40%, and on ImageNet, we only have 30%, which are far from satisfactory. So yeah.
But we don't have mathematical tools to measure the perceptual of humans, the bound differences of humans' visions.
Yeah, that's the case. However, we think that even though we don't have a tool to measure the closeness or the perturbation of human, maybe a threshold like here 8/255 is a relatively very small threshold, and even for this small threshold, the certified robustness is still very low. So I think it's a problem.
Yeah, I got it.
Yeah.
Thank you. I don't have further questions. Yeah, I think there seem no question in our chat box. Then this will be the end of our today's seminar. Let's thanks again for Dr. Lee come to us to give us great talk on his exciting works. Thank you again.
Thank you very much.
Yeah.
Thank you.
We also welcome you to visit us in Tokyo. Our office is in Nihonbashi station is the center of the Tokyo. It's near Ginza place. When you come to Tokyo, please visit us.
Oh, thank you for the invitation. I'll definitely visit your institute when I come to Tokyo.
Sure,
Thank you.
Sure, please. Thank you. Bye. Bye.
Bye.